Hey everybody, in this video we're going to look at image formation by a single planar interface by refraction. That's a mouthful. This image formation is sometimes known as the phenomenon of apparent depth. So let's see how that works. Now I'm going to call up a PowerPoint presentation again and just want to remind you that you can find it on our course page. Scroll down and these are posted. I think they're listed here in order as we go through the material, but you can see it right here, PowerPoint slides on phenomenon of apparent depth. Okay, so it's really cool, and again, if I see you in person, I can show you an example of this. Okay, so let me call up the slideshow, and I want to remind you guys that in general image formation, like we talked about with the plane mirror, we have the object sending light into the optical system, which has optical elements that change the paths of the rays, and then the rays, when they leave the optical system, they're going to form either a real image if they're converging or a virtual image if they're diverging. And we'll see that this single planar interface forms a virtual image. Okay, now here is a picture from a book showing some rays. We'll do the what I call official ray trace on the next slide. But in order for this to work, the light has to be in a higher index material refracting into a lower index material. Okay, so the light has to be going from high to low index. So in this picture, I'm emphasizing that N1 is greater than N2. So I want you guys to imagine an object point O. So this might be a point on the object. And here we're just drawing some arbitrary rays. So let's look at the first one on the top here. This one that's going right along this direction. So now it hits this interface. So we know it's going to refract. Now, since the light's going from high into low index, we know it's going to refract or bend away from the surface normal. So the surface normal for that incoming or incident ray is horizontal. So the ray, when it refracts, is going to bend up like that. And we do this with these other rays, right? And we notice that once they leave the simple optical system of this single refracting surface, planar surface, we see that the rays are diverging. So we sketch them backwards, trace them backwards, the diverging rays where they leave the optical system, and they appear to come from this common intersection point right here. That is the image point then for this object. So that is where the image is going to be located. It's a virtual image, and the only way somebody's going to see this virtual image, the eye or a camera has to catch some of these diverging rays. So your eyes got to be over here looking to the left, and you'll see this right here. Now this picture labels P the object distance and Q the image distance. We're going to do that in the next slide, but we'll also pay attention to the signs of those distances. Okay, and I mentioned this is known as the phenomenon of apparent depth because if you look at the image, it appears closer to the surface than the object actually is. And often these surfaces in nature are horizontal, like the surface between water and air is a classic example. So that's where the depth comes from. But there's a picture that shows you that a couple slides later. Let's go ahead and do the official ray trace. And since this is official, I'm going to have a horizontal optic axis. Here is my single refracting surface on my optic axis. I guess this should be centered. It doesn't really matter, but oops, sorry, but there it is. So I'm just going to emphasize that to the left of that is material 1, N1 index, and then to the right is N2. I'll put my object over here somewhere. I'm going to pick my same two rays. The first ray from the object tip, the tip of the arrow, parallel to the optic axis. Now we ask ourselves, what's happening here? We're not interested in the reflected light here. We're interested in the light that's going to go through. we're going to be using the law of refraction, then Snell's law. Well, the angle of incidence here, theta 1 in Snell's law, is 0. The surface normal for that ray is a horizontal line, right, for that vertical surface. So that means theta 2's got to be 0. So this light's going to go straight through. All right, not all of the light. Some of it is going to reflect, but a lot of it's going to go straight through. All right, so we finished tracing that ray. The next ray we always pick is from the tip of the object to this intersection point. There it is. Now, that ray, when it refracts, since the light's going from high into low, is going to refract away from the normal. So, whoops, sorry. So just sketch your ray when you're doing this on a piece of paper or on a test. You just bend it away. You don't have to be real precise. Just make it bend away like that. Okay. All right. So we've done the ray tracing here. We've got rays that are leaving the optical system. So then we ask ourselves, are the rays converging or diverging? Right, as they leave the optical system? Well, they're getting farther apart. They're diverging. So we trace them back. So the orange ray, if I trace it backwards, that's just going to go right back on the incident ray. And then this purple ray, when I trace it back, it's going to go like that. So the traced back rays are going to intersect right here at this point. So there is our image. So that is what the official ray trace would look like. Now we can label the distances. There is P, that would be a positive object distance from object to optical element. Notice this though, the image distance is always measured from optical element to image, right? So that is to the left in our drawing. So officially, that's a negative image distance. So if we were going to use some formulas to characterize what's going on, we'd have to be in tune with that. So that's a negative image distance, okay? There is the object height and the image height. Those are both positive, and yeah, in fact, they would be the same. H equals H prime, okay? All right, now, we can actually figure out what is that image distance for a given object distance. I'm going to do a little bit of trig. I want you guys to look at this triangle, and I have it drawn over here. I'll go over it with my cursor. It's the object arrow, and then the object distance, and this purple ray. You guys see that? That triangle? Here it is over here. So this side is H, this horizontal side is P, and I'm going to call the angle right here theta 1. Note that's the angle between the incident purple ray and the optic axis. Okay? Now there's another triangle I want you, and if you notice, the tangent of theta 1 opposite over adjacent is H over P. So H is P tangent theta 1. The other triangle I want you to look at is this one. It's the green image arrow, this horizontal leg, which is the image distance, absolute value, and then this dashed purple line. And that's over here. Notice that the left side is H prime. This other leg is the image distance Q, right? And then the angle between the refracted ray, let's go up here, between the dashed line and the optic axis, I'm calling theta 2 in this figure. But I want you guys to notice, the theta 2 between the dashed line and the optic axis, that's the same angle between the refracted purple ray and the optic axis. That's going to be important because that is the refracted angle theta 2 in Snell's law. Okay, now notice I can write that H prime is the absolute value of Q times the tangent of theta 2. And I'm just putting absolute value signs on here to emphasize that, well, Q really is negative if we're being sticklers. So I'll put absolute value signs. Okay, now, we know that H equals H prime. So I can equate these two equations, and I can end up with the image distance, absolute value, is the object distance times the ratio tangent theta 1 over tangent theta 2. Okay? Now, where that image point is located does depend on the incoming angle, theta 1, right, that this purple ray makes. Okay? And notice it also depends on theta 2, right? The angle that the refracted ray makes. So I guess what I'm trying to say is, where you see this image in terms of distance does depend on which rays are entering your eye. See, we've only drawn 2 rays, right? The orange and the purple, but there are a multitude of rays that are coming from that surface. All of them are diverging, and if you trace them all back, right, they're going to intersect somewhere, but they all don't intersect at the same point, it turns out. Okay, so if you're catching some rays that form some angle theta 2 with the optic axis, or near theta 2, right? That small group of rays where the theta 2 is close to the same, they'll intersect when you trace them back. All right, so if you're looking, let's say, using those values of angle, then you're going to see this image, right, maybe where it is in this picture. But let's say you go and use a different set of angles to view. So you move your eye up here, and now you're not catching this ray. That image location actually will move a little bit, okay? However, if the viewing angles are small, which means your eye is pretty much on the optic axis or not too far off of the optic axis, then all those ray angles are relatively small. And we can use Snell's law, n1 sine theta 1 equals n2 sine theta 2, and the fact that for small angles, sine of theta is approximately tangent of theta. So what you can do is you can replace the tan thetas in this formula with sine thetas. So you get Q is approximately P times sine theta 1 over sine theta 2. But by Snell's law, the ratio of sine theta 1 over sine theta 2 is n2 over n1. So if you're viewing the image with your eye near the optic axis, not too far away, so you're viewing small refracted angles, then the image will appear to be about at the same place. Even if you move your eye a little bit, as long as the angles remain small, and we're typically talking like 30 degrees or less, so it's really not as small as you might think, then you're going to see the image pretty much at the same point. But if you swing your eye off the optic axis, and now you're using ray angles that are near, 60 degrees, this image will actually appear closer to the surface, or I should say, the interface, okay? In fact, as you increase your viewing angle, the image gets closer and closer to the interface. Okay, well, let me go to the next slide, because it does show a fish. So here is somebody viewing, for instance, a fish in a pond or an aquarium straight down. Okay, and again, this just shows how the image is formed. So this point on the fish here will be imaged up here at this yellow point. So the actual object distance, or depth, if you will, of the fish, we label D in this picture. The image distance is Q, right? And the fish will actually appear to be at this depth of Q, really absolute value of Q, again, if we're sticklers, okay? While the actual depth is D, and that apparent depth does depend on the viewing angle, but for small angles, so when you're looking straight down on the fish, here's that formula that we developed in the last slide. Now, if this guy starts moving his eye, let's say to the right, and the fish is still here, now he's viewing the fish. He's got to be catching rays that form much bigger angles. Well, what will happen is the image of the fish will actually get closer and closer to the surface. So if he's looking at this fish with his eye way over to the right here, where he's catching refracted rays that are forming really big angles, it'll appear that that fish is right near the surface. You may have had this experience if you've ever looked at an aquarium, not from down from the top, but just look through the glass of an aquarium. If you're standing right in front of, let's say, the fish, and you're looking at it through the aquarium glass, the image does appear a little bit closer to you. You're really not aware of it, though, if you're looking straight ahead that much. But if you now, let's say, walk to the left, and you're still looking at the same fish, and assuming it's not, it hasn't, it's still there in the same position, it hasn't swam away. But if you look at it, you'll see the image of the fish much closer to the glass of the aquarium. Okay. Anyway, another place you may have seen, experienced this is if you've ever gone swimming, and let's say you're at the deep end, right, and you're on the diving board about to jump in the pool. When you look down at the bottom of the pool actually appears much closer to you than it actually is. In fact, if you do this ratio, air index of 1, water index of 1.33, N2 over N1, right, that's about 3/4, right? Yeah, because N 1.33 is like 4/3. So the depth is about 3/4. The apparent depth, the image distance, is about 3/4 of the actual object distance. So if you're looking down and the actual depth of the pool is 10 feet, it'll appear that it's about 7.5 feet, okay, instead of the actual 10 feet. Okay, all right, I've blabbered enough about that, and I'll stop the video, okay? But that's the phenomenon of apparent depth. Okay, bye-bye.